Hello, so in this video we're going to look at section 1.3, rate of change and behavior of a graph. We're going to be looking at two different topics. In the description below, there will be the video chapters, so you can jump to the various sections you would like to see. There will be a link to the Openstax textbook, the first and second edition. There will also be a shared folder that you're welcome to look at and view, along with a survey at the bottom. So first, we're going to look at finding the average rate of change, or just the rate of change. So the rate of change describes how the outputs change within the inputs, and this is just the slope of our graph. And so the average would be between two inputs, and the outputs would be divided amongst them. And so to find what our slope would be, we would just take our outputs divided by our inputs, and that would give us how far we're going up and down the graph, and then how far we're going left and right on the graph. So let's look at finding average rate of change for these 2 points that were given. So we could label the points that were given x1, y1, x2, y2. We could look at either of the formulas, so you're going to see either ones typically. I personally prefer the y2 minus y1 all over x2 minus x1, but just a matter of how the syntax of your book is or the situation that you're given. So if we looked at the first way, we can look at f of x2 minus f of x1 all over x2 minus x1. We know that for an input of 2, and we're also going to have an input of -1 all over 2 minus -1. If we plug in the values for this, we know that we're going to have 1 minus 4 all over 2 minus -1, and our slope would be -3 over 3, or just 1. We could also look at y2 minus y1 all over x2 minus x1. And so we would have this delta y, or the change in y, all over the change in x, equaling y2 minus y1 all over x2 minus x1. We plug those values in. We get 1 minus 4 all over 2 minus -1. We can see that we get a -3 over 3, and we can just round it to a -1. And so our simplest form of our slope would be going -1, +1, -1, +1, and we would see that it would be a downward slope or a upward slope from the left. So now we want to find the average rate of change based on the function that we're given. F of x is equal to x squared minus 3x plus 1 on the interval including -3 to including 4. So we could look at this being 1 point. So we could consider -3 for 1 point, but we also want to get another set. So we could take -3 and 4 as inputs, and then we're given -3 is one of our and another point, and then we could do 4 and another point. So if we looked at our function, we could use f of x equals x squared minus 3x plus 1. Plugging in a -3, where we see an x, we get -3 squared minus 3, -3 in parentheses plus 1. If we plug that into our calculator, we can see that we're going to get an f of -3 is equal to 19. And so we would have the point -3, 19. If we plug in for 4, we can see that if we go f of 4 is equal to, in parentheses, 4 squared minus 3 in parentheses 4 plus 1. If we plug that into our calculator as well, we're going to see that we're going to get equal to 5. And the order pair would be 4, 5. So now we have our x1, our y1, x2, y2. We can plug those in and see our slope. So y2 2 minus y1 all over x2 minus x1. So 5 minus 19 all over negative 3 minus 4. And we're going to get negative 14 over 7, and that simplifies to a negative 2 over 1, or just negative 2. So next we're given, find the average rate of change for the expression f of x is equal to 4x squared minus 7 on the interval in brackets 1 to m. So in these kind of situations, it's easier to use the function notation. So you can plug it in for a value for the 1 and the m, versus if you have two given points, you can use the y1, y2, and x1, x2, and kind of do the calculations that way. So if we plug in on the interval for 1 and m, so we have the change in y over the change in x. If we plug in the values that we have, we are going to see that we have an m minus 1 on the bottom, and then we're going to have in parentheses 4m squared minus 7. Another set of parentheses, we're going to have 4 in parentheses 1 squared minus 7. In the top, we're just going to get a 4m squared minus 7 minus a negative 3 all over m minus 1. If we combine like terms, in the top, we're going to get a 4m squared minus 4 all over m minus 1. If we factor up top and we pull out a 4, we're left with m squared minus 1 all over m minus 1. And we can see that it's a difference of squares. And so we would have 4m plus 1, m minus 1 all over m minus 1. And we can see that our m minus 1s would cancel, and we are left with 4m plus 1. So now we want to find the average rate of change for the expression f of x equals x squared minus 3x plus 1 on the interval from x to x plus h. And so this is how we would set it up. And so all we would have to do is plug in our function for f of x in for everywhere we see an x, and then we would do the same thing for x. We would do the same thing for x plus h and x, and then combine like terms to FOIL and just get in terms of x plus h. So if we put it in terms of, for the function notation, we would have in parentheses x plus h squared minus 3x plus h plus 1 minus, we would keep our x squared minus 3x plus 1 all over our x plus h minus x. If we were to FOIL our x plus h squared, we would get an x squared plus 2 hx plus h squared. And then if we would distribute our negative 3x into our negative 3 into the x and the h, we get minus 3x minus 3h plus 1. And then we would keep our second one all over our denominator. And since we can combine like terms, we can see that our x's would cancel and we're left with h. We would also want to distribute this negative into our quadratic on the right. And so we would have x squared plus 2xh plus h squared minus 3x minus 3h plus 1 minus x squared minus 3x plus 3x minus 1 all over h. If we combine like terms, we will get h squared plus 2xh minus 3h all over h. If we factor out an h in the top, we would get an h plus 2x minus 3 all over h. We can see that our h's would cancel, and we would get for an answer 2x plus h minus 3. Now we're going to determine where a function is increasing, decreasing, and being constant. So first, let's look at increasing. So we can see that increasing, we would have 2 points on our graph that would be like a window where A would be higher than B on the points on an x-axis, and that would be considered increasing. So if we use this one and this one as our points, we can see increasing would be right here. Then we can also look at decreasing. So if we looked at points from here to here, we can see right down through this slope that would be decreasing. And so it would be the same window between A and B. And the increasing and decreasing can be multiple points on a graph, and you would determine those in interval notation as your answer. Then we get to the idea of a local max and a local min. And so for a local max, we would be on the topmost point of our graph. So if you had upside down parabola, the topmost point would be right here. And so it would be increasing here, decreasing here. And then we can do the same thing for the local min. We would have the bottommost point, for example, for a parabola, we can see that it would be decreasing here, and it would be increasing up here. So now we want to determine where the certain functions are happening, so where it's increasing, decreasing, and constant, and we also want to find out where the local max and local min are. So we know that we're going to look at our domains. So from left to right, we're going to see where it's increasing and decreasing, and then we'll go back and see where our local max and local min are. So for increasing, we can see from negative infinity to -4, we're going to be increasing. And then we can also see that we're increasing from -1 to positive infinity. And so we can write it in interval notation, making sure that we're using parentheses for infinities. So going from negative infinity to -4, we're increasing. And we're also increasing from -1 to positive infinity. We can see that we're decreasing from -4 to -1. We can see that we have our local max up here at -4, 5. And we can also see down here where we have our local min, and it would be at -1, -4. So now we're going to look at, for this graph, the increasing and decreasing max and min. So we can see that from left to right that we're decreasing here and we're increasing over here. For increasing, we're increasing from 3 to positive infinity. We're decreasing from negative infinity to 3. We don't have a local max, and our local min would be right here at 3, 2. So now we want to look at this graph and see where it's increasing, decreasing, and constant, along with the local max and local min. So we can see from left to right that we're increasing from -3 to 1. We're also increasing from 0 to 1. And we're also increasing from 0 to positive infinity. So for increasing, we would have -3 to 1, union 0 to 1, union 2 to positive infinity. We can see for decreasing, we're decreasing from negative infinity to -3. We're decreasing from -1 to 0. And we're also decreasing from 1 to 2. So for decreasing, we would have negative infinity, -3, union with -1 to 0, union from 1 to 2. So for a max, we can see that our maxes would be at 1, 2, and -1, 1. We can see for our local min, we have 3 of them. We're going to have 1 over here, and down here. So for our mins, we would have -3 and -2. We'd have our origin, 0, 0, and we would also have 2, -3.